extend from 4 parts. The first part is the introduction, the background, problem statement, and objective. Forest fires in Southeast Asia occur frequently, causing severe impacts on ecology, society, and economy. Although satellite remote sensing technology, particularly the moderate resolution imaging spectrophotometer, have significantly advanced the ability to detect and monitor fires. There are data gaps and uncertainties requiring special interpolation to estimate fire-related parameters at unsampled points. Sarawak, Malaya is known for its vast tropical rainforest, plainland, and agricultural lands. In such a complex environment, the fire hotspot data in the Sarawak region exhibition high spatial and temporal variability. This figure shows the fire hotspot data of Sarawak, Malaya in July 2021. This obtained from Fire Information for Resource Management System. The red dots in the figure denote individual fire hotspot identified by satellite-based thermal anomaly detection. It shows weather spread and unevenly distributed fire active in Sarawak. This is caused by the spatial distribution of fire hotspots is strongly influenced by land use and ecological features. Fire hotspot monitoring is a crucial component of environmental management and emergency response systems. Fire predictive power, a key indicator of fire intensity, which correlates with contribution intensity and emitted energy. Accurate spatial interpolation of FRP is crucial for early warning systems and the effective deployment of firefighting resources. Among various spatial interpolation technologies, the inverse distance weighting method is widely adopted due to its simplicity and effectiveness in many geographic information system applications. Then let's dive into the challenge of the research. The traditional IDW interpolation method uses a fixed power parameters throughout the entire dataset, which assumes spatial uniformity in the influence of nearby data points. In most particle applications, the fixed power parameter is set to by default. A convention that often oversimplifies that spatial variability inherent in complex phenomena such as forest fires and linked to inaccurate estimation. Moreover, exciting most for selecting power parameter are mostly arbitrary and train and error, taking a data-driven assessment approach. Given this issue, here are 4 objectives. First, to apply Monte Carlo and K-Ford consolidation approach on fire hotspot data in Sarawak, Malaysia. Then to determine individual power parameter for each data split based on the lowest rounding square error from predefined IDW power parameter. Next, to optimize the IDW power parameter using gradient descent starting from the initial power parameter. Finally, to compare the interpolation performance of optimized and fixed power parameter IDW models using mean square error. Next, The second part is methodology, which including research framework and most. The research framework connects of 5 main phases. First, acquiring the fair hotspot data in several malaria from the model fair occur. Second, performing in multiple keyword and Monte Carlo consolidation runs. Third, identify the most appropriate initial power parameter based on RMSE. Fourth, estimating the best IDW power parameter using gradient distance. At last, comparing the enhanced IDW model with the fixed power parameter IDW model. Next, let's explain in detail. The dataset used in this study is obtained from the moderate resolution imaging spectrodiometer, where a chart hosted by National Aeronautics and Space Administration Fair Information for Resource Management System. A total of 550 related fair points in Sarawak, Malaysia are written for interpolation modeling with 30 data points selected from each year between 2018 and 2022. Each fair detection record includes latitude, longitude, and FRP. To evaluate the robustness and generalization capital of IDW interpolation, this study applies to widely used consolidation technologies. One is the keyword consolidation. The 30 data points for each year are divided into 5 folds, with 6 fold points in each fold. In each consolidation, one fold is used as the testing site, and the remaining folds are used for training. Another is Monte Carlo consolidation. For each year, 10 points are randomly selected as the testing site, and the remaining 20 points are used as a training site. This producer is repeated 5 times using different random sets. Monte Carlo consolidation complex keyword consolidation by offering diverse random partition, which are particularly useful when the dataset may exhibition spatial imbalance. Understanding IDW is key to the research. IDW is used to estimate unknown values at assembled locations based on the known values at surrounding points. The fundamental assumption is that nearby observations have greater influence on the prediction than those farther away. As a reminder, IDW weights nearby points more strongly. The power parameter contrasts this statistic, but how to adaptive find the optimized parameter? That's where gradient distance helps. MSE between actual MSE between the actual FRP values and the interpolated values generated by the IDW model, with power parameter is used as the loss function for the gradient descent boson. The updated rule for power parameter in each interaction is given by the standard gradient descent formula. To ensure effective convergence and prevent unnecessary integration, the stopping center used in this study is based on the change in loss function between successive interactions, especially the gradient descent optimization process is terminated when the absolute difference in MSE between two convergence interactions is less than a small result. Yeah. Alpha in this is that the learning rate needs to be adjusted methodically. To ensure efficient convergence and create unnecessary integration. The stopping certain used in this study is based on the change in loss function between successive integrations, especially the gradient descent optimization process determined when the absolute difference in MSE between two convergence integrations of less than the small. The third part is the research result. Now let's look at the result of initial consolidation. To evaluate the influence of the power parameter on IDW interpolation accuracy, a range of values from 0.5 to 3.5 with a gap of 0.5 is tested using both K-fold and Monte Carlo consolidation modes. This table displays the RMSE results for each fold of the 5-fold consolidation in 2021. This table is for Monte Carlo consolidation. Both two tables show that the optimal power parameter differs significantly across for the refocusing and a conclusion that affects the global power parameter is inadequate. Then let's focus on the process of gradient descent. In most gradient descent interactions, the error decreases rapidly in the initial interactions and generally converges to a stable minimum, inducting effects convergence behavior. Although the starting point and the convergence point vary slightly between different folds, the overall trend indicates that the gradient descent algorithm effectively minimizes interpolation loss by adjusting the power parameter. Gradient descent has both small and large power parameter changes, but all of them can dynamically switch for a locally optimal power parameter. Next, let's look at the result after gradient descent iterative optimization. The table comparing the enhanced IDW model with the traditional IDW that affects the power parameter at 2. The MSE error of the enhanced model is significantly better. Therefore, the enhanced IDW model turning yields the more accurate and reliable interpolation. The last part is the conclusion. This study optimizes the IDW power parameters through a combination of consolidation technologies and gradient descent optimization, improving the FRB interpolation accuracy of fair hotspots in Sarawak, Malaysia. The results show that the fixed power parameter is not suitable for especially heterogeneous data, while the data-driven optimization modes can better adapt to complex spatial patterns. The improved IDW model enables automatic and effective power parameter tuning without relying on train and error modes, offers better prediction of fair intensity patterns, supporting early warning systems and resource allocation in fair region. According to the limitation, here are some recommends for future work. First is explore or adaptive learning right stages for gradient distance can be explored to improve optimization effects. Next, a real-time interpolation system can be developed combined with real-time satellite data to support fair monitoring and emergency response at last extended to other spatial data analysis fields such as hydrology, agriculture, and urban planning. These are my references. That's all. Thank you for your attention.
Okay, thank you, Chen Mohan, for the presentation. My first question is on your data set. So you said that you have 150 points.
Yeah.
But why you choose only 30 points for each year?
I chose 30 data for each year. I have 5 years, so it is 150.
In total?
Yeah, in total.
Not for each year you only have 30, so in total you have 150.
There are many data in a year.
You have many data in a year,
Yeah.
and why you only choose 30? Because you are doing optimization, prediction, right? And
Yeah.
you use very small data, 30 points only. Why you choose only 30 points? See, you already have a big what is the size of the data?
Because a year is so long. On the different time, they have different data. So I chose 30. I think it is enough.
You means each year you have different points? Is it?
Because in different time they have different data.
Okay, and then?
So I chose the 30 data is for a month of a year.
Okay, because the size of data is very small for your study. Okay, so it's quite difficult to decide, to make decision which parameter, which method is good for your study. But then okay, so you choose 30 points for each year.
Yeah.
Okay, and then you apply cross validation.
Yeah.
And 5 cross validation, 5 full cross validation. Why you choose k equals to 5?
Because this is normally use k equal.
Are you sure?
Yeah.
But based on my reading, the common value is k equals to 10.
Because for 30 data equal, I chose k equal to 5. Well, 6 data for testing and 24 for training. But if I chose k equal to 10, there are only 3 for testing and 27 for training.
Yeah, is it acceptable to use k equals to 5 for your data?
Yeah.
For larger data, k equals to 5, you will get
It's
very
a
large
base
error.
yeah.
Yes, you should try from k equals to 10. Okay, so in your dissertation you said that k equals to 5 is the common value, but it is wrong. It's not a common value. It is acceptable value for your data. So you have to explain why you use k equals to 5. Okay, and then okay, so I don't have any comments on your result based on the validation, cross validation, but my concern is on your model validation. Can you explain how you validate the model?
The model validation is that this is the optimal P that I use gradient distance to get the P, and I have the MSE for the P. This and the traditional IDW is just P equal to 2. This is for P equal to 2. I compare this.
And how do you get the MSE value?
I calculate
based on the fold?
based on cross validation.
Cross validation, the 5-fold and the Monte Carlo.
Yeah.
I think that's not the correct way how you validate the model, because you use the MSE value from your cross validation previous how you use cross validation to get the P value, right? To optimize value of P. Okay, so that's another method, the cross validation. You cannot use the same result to validate your model. It's biased.
For this, I just wanted to compare the performance of the gradient distance.
Yeah, but then you said that you want to validate your model. So you cannot use the results from the cross validation to optimize P to validate your model. It's a bias. This is not correct way to validate your model. So the best way is you have to use the nested cross validation. This is the gold standard for cross validation. Have you heard about nested cross validation?
What?
Nested cross validation.
Another cross validation.
The same cross validation, for the fixed value, optimized P and optimal P. But you do it again by using the nested cross validation. You cannot just take the MSE value from the previous run, because the previous run is to optimize the P. Okay, so this one is to validate your model. So you have to use the nested cross validation. Okay, talk to your supervisor about this method, how you can validate the model. You cannot just take the MSE value from the optimized P, because you're going to compare with the fixed P and the optimal P. So this is bias comparison. Okay, same goes to Monte Carlo. Okay, so you have to improve this part. I think that's all from me.
Okay, thank you.
You have prophesied.
First page, your title should be less than 40 words, I think.
Okay.
So your title is very long, and then your UKM style in the references is not correct, so you should check again.
Okay.
Maybe I ask you one question regarding the content, the gradient descent algorithm. So in that algorithm, you calculate the derivative, right, of the loss function.
Yeah.
Exact, using exact expression formula.
Yeah.
Exactly. How sure are you about the smoothness of the loss function? If your loss function is not smooth, how do you calculate the exact derivative?
I calculate in the size.
Right, you use the exact expression for the derivative, huh?
Yeah.
From your data, you get the loss function is very smooth. How sure are you that loss function is smooth and differentiable?
It is not smooth. It's just for global optimization. For different start P, it maybe get different optimizations, but it optimize the facts better than facts the P.
Okay, one last question. Your gradient descent algorithm, can it converge to local minima?
Local minima?
Not the global minima, but local minima. How you do avoid the situation convergence to the local minima? Never mind. I'll send you, email you my comments so you can discuss with your supervisor. Okay?
Okay.
I'll email to your UKM email. Okay?
Thank you.
Okay, thank you.
Thank you, Chen Mohan. We will proceed with Hamza.